All right, so I'll cover most of the pre-processing steps, which is performed on the data set. And as I have mentioned, for resting as well as task, they're very similar, right? So there are some differences. I'll try to cover them as we go along, right? So these are, okay, this is not really pre-processing step, but typically we try to find like the head motion, you know, do motion correction, then do alignment of functional and anatomical data, and then alignment of anatomical data to MNI space, and then alignment of functional to MNI using the same affine transformation which was used to align anatomical to MNI, right? And although even if you don't have anatomical, you can always align them to the MNI template, but obviously higher resolution will make the transformation to the MNI space better, right? And then how do we create a design matrix for task activation, and then regression of task and motion. So perhaps like as you design your experiment, or even when you're doing resting state, like what is signal and what is noise depend on the question you're asking, right? For example, if you want to scan people who are addicted to drugs, you can collect resting state for healthy subject and drug abusers, and then you can find differences. But sometime in like drug abusers, the heart rate and respiration rate is, I wouldn't say like has a different frequency, but the variability is very different, right? So some say that just by looking at the heart rate and respiration rate, you can have some sort of prediction whether this person is a normal person or not, right? Again, the point is that depending on the question you're asking, what is your signal and what is your noise is dependent on that, right? So if I wanted to ask what is happening to respiration rate if I'm breathing 2% CO2, then the respiration signal is a signal of interest for me, right? But if I want to say that, okay, I don't want to see the effect of respiration, I just want to see how does the functional signal, this low frequency functional signal is affecting my correlation, then the respiration, you know, is noise for me, right? And based on the example we did yesterday, if we have 4 predictors like left hand, right hand, left foot, and right foot, then the design matrix, which is our fMRI, the fMRI signal is the design matrix multiplied by the betas plus the residual, right? So these are the different, so we have to find the weights corresponding to each of these signals, right? So in some way you can think of correlation as a very simple GLM analysis where you have only one regressor, right? You have only one signal of interest, right? With correlation, you're taking just X and Y, right? So this is X and this would be Y. While when you are doing general linear model, you can have X equal to beta 1 times Y1, beta 2 times Y2, and so on. And then the residuals are things that we cannot explain. So for fMRI, the minimum number of residuals is how many? Like the default, right, is how many? From the two examples we did. Any guesses? Yeah, right, 9, good. So what were those? So the motion parameters and then like drifts, right, and a constant term. So the residuals is basically what we cannot explain, but these are not of interest. So we are just trying to model this to this signal. Okay, is this clear to everyone? Okay, and so this is like if there was a body, face, hand, and scrambled object, then let's say the beta was these value and these were the standard error, then we can find the t value and consequently the p values, right? So the beta plays a role. Also, the noise estimate also plays a role, right? Because in this case, this is constant. This one plays a larger role, right? Because this is constant, therefore, the larger the beta value, the more significant it is, okay? So that is how we can find differences. So SE is the noise estimate for contrast, and signal divided by noise is basically how we will look up, right, find the T, and then from this, assuming a Gaussian distribution, we will find the corresponding p-value, right? Does everyone know what a Gaussian distribution is? One second. Can someone explain? Maybe Shivani? How about you? Okay, so how does it look like? What is it called? Okay, it's general. Okay, what is it called? The bell curve, right? Yeah. Anyone else who can explain what a Gaussian distribution is? Very good. Right. Very good. Right. So assuming that it's a white Gaussian random noise, then they follow a Gaussian distribution. The good thing about Gaussian distribution is you need only two parameters to define a Gaussian distribution. And what are those parameters? Mean and variance, right? And if you have mean plus minus variance, what percent of the distribution can you account for? Hmm? Very good. Is it 64 or 6? Is it 64 or 67? Uh, uh, okay. And then 2 times the standard deviation, it is 90 something. right? And so so okay, so everyone knows, right? So let me ask a quick question. So let's say there are two students in a class, no, two students in a university, and one person took physics and got 85. The person who took biochemistry got 90, right? Who is a better student? Or do you need any additional parameter? The what? The mean, you mean? The, oh, right. So, right. So if you, let's say I could not give you all the students mark, it would be like mean would be good. So let's try, right? So let's say student A gets 85 and student B is 90, right? And the mean was mu is let's say 80 and the mean is 95. From this, can you tell who is a better student? Like who did better in the exam, maybe is what I want to mean, right? Or do you need any other variance, right? Okay, good. So let's say the variance of this is um, equal to 10, and the variance of this group of student is 5, right? Can you now tell who is a better student or who did better in the exam? Who? So the mean is 80, the variance is 10. The mean is 90. The mean, okay, no. Let's make it 80. Okay, let's say the mean, maybe it's easier. So the mean is, for both the cases, the mean was 80. In the first one, the variance was 85. In the second case, the variance was 5. So who did better? So this person did better, right? Because the mean is 80 and this person has done 2 times the standard deviation, while in the first case, it's not even 1 standard deviation, right? So similarly, in fMRI, any measurement that you are making, um, you have to have not just the information of the mean, but how much the variance is. And again, like as I've been trying to mention, what are the sources of variance in fMRI signal? What are the main sources of variance in a fMRI signal? Shreyans, what are the main sources? Hmm? Respiration? Did you say respiration? Okay, so physiological noises are like one one source. Head motion is another one. Can you think of a third one? Oh, very good. Okay, okay. So individual differences are one, but what, how, like, what are the sources of these? So, okay. So Okay, very good. So what does that, so what would give rise to variation based on location? So it's the underlying hemodynamics, right? So the main sources are physiological noise sources like heart rate and respiration. The second one is motion, and the third one is the underlying hemodynamics, right? So those are the main ones. I think as she's mentioning, there are also individual variations, um, but like after you account for this, there would be some individual variations, right? And so what we have to do is try to minimize for these noise estimates for contrast, right? So these increase, right? And as these increase, your statistics will get worse. The t-value will decrease. Is if your noise residual power increases, right? Like motion parameters, physiological, and that if the correlation between the different predictors, there is correlation, or if the degree of freedom is reduced, right? Does anyone know what a degree of freedom is? Uh, right, right. So let's say we collected 800, let's say 104 data points. So what would be the typical degree of freedom for that data set? Good, right? So that is the assumption, and the assumption would be that each time point is independent of the other time point. When that is not the case, the degree of freedom would be less, right? So how can the degree of freedom be further affected? If we do, how can the degree of freedom be further get affected, become lower? So it would become lower if you're doing temporal temporal smoothing or spatial smoothing, right? So when you do any kind of averaging, like um, sequential data points are no longer independent. So therefore, the degree of freedom would be reduced. So the degree of freedom, if you are collecting a data set, um, then the number of data points that it has, you should subtract. Like if the data that we collected has 104 data points, then the degree of freedom is 103. That is assuming that each data point is independent of the other data point, right? It would be like uh, something which is completely unrelated, right? Let's say, can anyone give some examples where you can think it would be like your um, like date of birth, for example, of different students in the class, right? So it should be fairly random, right? However, if I asked year of birth, then perhaps it's not so random because it's like most of you. So, so when we are estimating the degree of freedom, we would like the degree of freedom to be high, right? If it goes down, then our error increases, right? So how can we improve our statistics? Um, the easiest way is to increase our signal, right? And of course, like you cannot change, the 3 Tesla and put a 7 Tesla. But what you can do is try to improve based on the imaging parameter, right? One way is slice scan time correction. We had um, discussed before how the data is collected, um, like 1, 2, 3, 4, or 1, 2, sorry, um, 1, 3, 5, 7, 9, and then 2, 4, 6, right? So in that way, um, the other way is to reduce the residual noise, right? And that can be done using motion correction, spatial smoothing, high pass temporal filtering. Again, high pass temporal filtering would simply get rid of the high frequency noise component. Also moving variance from unexplained noise to explained, right? Predictors of no interest, like motion parameters, signal from noisy area, white matter, CSF, and so on, right? So there are um, two ways as to how it can be done. And one is pre-processing of data before running GLM. That is one way. The other way is to include um, like um, this signals of no interest in GLM, right? So some of the known noise sources is a linear drift, right? You can have a stimulus like this, but if you look at it, there is a trend, right? And one way we can address it is by saying that, okay, there is a linear trend and we are going to remove the linear trend, right? And that is easy to do. And there are several causes of linear trend. One is that when you're collecting data in MRI, the gradient slowly heats up. And as the gradient heats up, the signal will become lower, right? So when you are doing the scanning, if anyone is to collect fMRI data, just scan a phantom for like 15 or 20 minutes several times and see if you observe a drift, right? And if you observe a drift, then you should complain to whoever your scanner manufacturer is, right? So with this one, this would suggest that there is, if this was obtained from phantom, then it would suggest that there is something um, which is affecting the signal and the signal is going down. Right? So in this case, what you can then do is you can remove the trend and then look at the signal again, right? So you have basically removed a linear trend. And so this would fit with the signal better, right? So in this case, this is of interest, like predictor of interest, and this is predictor of no interest. So then in our GLM, this would be used for our beta estimation, while this would be used for noise regression. Okay. And as I have said, when you have head motion, the easiest way to know if there is motion is to look at the edges. And if your edge, if your activation, in addition to lighting up some region, is lighting up the edge of the brain, then it's very likely that this data has head motion, right? And how would you correct for head motion? What command would you use? Hmm? Which one? MC McFlirt, right? For um, FSL, like for AFNI, it's called 3D Volrex. So there are again different um, programs which exist to correct for motion. So it should be used to correct for motion, and then you would get at least 6 parameters which you can use for predictors of no interest, right? So you would use this. Um, Also, people have started using another parameter called FD, frame-wise displacement, also as a predictor of no interest, right? So in this case, you have 4 predictors of interest and 6 predictors of no interest, plus a constant, right? So the pros and cons of motion regressor is that if motion artifacts are not correlated with your paradigm, and thus with your predictors of interest, then motion predictors of no interest improves the data, right? Because these are, you are showing that the person like moved due to like moved unrelated to the task, right? Maybe the person become sleepy or so and slightly tilted their head and had nothing to do with the task, and therefore you can use it as predictors of no interest, right? So you use the noise sources and then use it as predictors no interest. However, if you know, as I was mentioning yesterday, if you gave the task and the task condition was such that the head motion happened because of the task, then you are in trouble, right? Because then separating the head motion from your activation is not going to be easy, right? So as I was mentioning yesterday, if you had asked your participant to lie in the scanner and told them, okay, when I say tap, you do like this, then very likely, right, when they move like this, it will induce some head motion, right? And to remove that from um, the task induced response is not going to be that easy. Okay. Um, does anyone remember how just by looking at a fMRI time series, you can tell if a person, if it was head motion or if it was task response? Huh? Okay, by looking at the time series, by just looking at the time series. Hmm? Okay, what were you saying, Shreyans? That so during motion, the signal change is abrupt, right? And it will look like spike. While if it is due to um, neuronal response based on the task you're doing, the response is going to be gradual, right? So that is like one way to detect. But as I've said, the easiest way to detect is just by looking at the data. You can make a movie or toggle between the first image and the last image, and it will give you a decent understanding as to, you know, how the data looks like. So one way in which we can increase the signal intensity or signal correction is called slice scan time correction, right? And the slice scan time correction um, is in the following way, right? So this is non-interleaved descending order, right? So let's say your TR was 2 seconds, like the sampling rate is 2 seconds, and you have 20 slices, right? So what it means is that the data is collected here, time 0, here at time 100 millisecond, 200 millisecond, 300. Here it will be 2 seconds, right? So just if you looked at the data on this slice versus this slice, how much difference there is going to be in time? How much? 1.8 seconds, right? If it is 20 slices, if it's 20 slices, sorry, 1.9 seconds, 1.9. If each one is getting collected at like 100 millisecond, 200 millisecond, 300 millisecond, then between the first one and the last one, there is going to be almost a 2-second difference, right? So just as an example, if you were to, let's say, study motor, how it affects not only the primary motor, but also the cerebellum, it would tell you incorrectly that between motor and cerebellum, there is a 1.9 second delay, right? But which is not the case, right? So this is because of how the data was collected. So we have to correct for that, right? So this is one way. The other one is interleaved descending, right? So as I was saying, it would be like 13579 all the way till n, and then again 246, right? The trouble here is that between slice 1 and slice 2, how much will the difference be? Between slice 1 and slice 2. Okay. 1, 3, you know what I mean, right? The data was collected 13579 till 19, then it went to 246 till 20. So what is the delay between slice 1 and slice 2? Very good, 1 second, right? Because it took 1 second to collect all the odd number, then to go to 2, like you would have spent 1 second. So between slice 1 and slice 2, there would be 1 second, right? Between slice, yeah, there would be 1 second, and so on. So again, like one has to be careful. For like resting state, it doesn't matter that much because we are looking at low signal. But if you were doing task activation, you have to be very careful, especially if you're looking, let's say, wanting to do memory or something where the effect is small, then you may get a false idea that there is a large delay, right? So then now there is this new technique called multiband. And in multiband, what you do is you collect simultaneously, right? And because you're collecting this data simultaneously, therefore, the correction that you have to use is more complex. Right? So in this case, even with, the reconstruction has to be done accordingly. Again, the point is that when we were analyzing the data, in the header information, it showed the data structure, and one of them had how the data was collected, interleaved or simultaneous, right? So that information is in the header, so you can do the correction using different methods. Example where they are showing how like time since event onset, and this is time since, like, with and without correction, how the signal would look like, right? If the distribution was like this, you did not do any correction, then the response may look like this, right? And it's not just the amplitude, it is also the delay, right? Which may give you a false information. So we have to always correct for these kind of changes. So the way it does is that for slice scan time correction, this interpolates the data from each slice such that it is as if each slice has been acquired at the same time, right? So what it does is that it takes the first slice as the reference. If the second slice was collected 100 milliseconds later, it will use a time shift by 100 millisecond, right? And for the third slice, it will do a delay by 200 millisecond, and so on. Again, based on how the data was collected, right? If it was collected sequentially, then it will do it in that fashion. If it was done in an interleaved fashion, then it will do it in that fashion. Again, sometimes this slice time in correction is not very easy to do because it may interact with the motion correction, right? Because if you do interpolation, the motion affects multiple volumes instead of just one, right? So just doing a time shift may not work properly. But with multi-band sequences, one can do the whole thing, collect the whole data within a second. So sometimes, like, these problems can, like, it doesn't become much of a problem as with, you know, TR of 2 seconds or higher. So increasing signal and decreasing noise, and the way it can be achieved is through spatial smoothing, right? This is without any kind of interpolation, right? This is 2D without any interpolation, and this is one-dimensional signal without any kind of interpolation. So this is, if this is how your voxels in, if you look at the image and you look through one line of the image, let's say this one, and the intensity looks like this, then with smoothing, what is done is you use a Gaussian kernel, right? And what we use is called full width at half maximum, like 6 would mean that full width at half maximum, this would be 6, right? And you use this as a filter and do it for from the beginning to the end, right? So what we are doing here, right? So what we are, can anyone explain what we are doing here? So we have a Gaussian kernel which has several parameters, and then we are convolving this with the entire line of the image. Okay. Is that clear? No. So in here, what we do is initially we will start from the beginning, and that value would be given as this one. 0.1 is the first value, second value is 0.3, third value is 0.75, fourth is 1, fifth is 0.75, 0.3, and 0.1, right? So it is a symmetric values that we are adding, right? It's called convolution. But what we are doing is we are using this formula where we are taking every, let's say we start with this one, right? With fourth one. So the fourth value is, let's say, 40. 40 multiplied by 1 times 0.75. The third value plus 0.3 with the second value 0.1 with the first value. Then for the fifth value, we will multiply by 0.75. Then the sixth value with 0.3, the seventh value with 0.1. So what it does is it gives any time series or voxel, we are changing the current value with 3 values to its left and 3 values to the right and averaging, right? So this way, our signal to noise ratio is to go up, right? Because like it is dependent on all these values, right? And then we do this, like we start from the beginning, and then we will compute the new value for the fourth one, then shift it by 1, recompute the value for the fifth one, sixth one, and so on. For each one, there will be 7 multiplication, 7 addition, and we will replace the value as we go, and then we will have a new averaged time series, right? So this process is called convolution, right? Or maybe some of you may have heard of moving average. Anyone has heard of moving average filter? Yeah. So right. Yeah. You, you use ARIMA model in stock market? Okay. So I think ARIMA model is autoregressive moving average, right? So this one is like you can think of it as weighted moving average, right? Or you can think of it as Gaussian filter, because a simple moving average would be you take 1/7, every value would be 1/7 if you have 7 elements, right? And then you add them up. But this one, we are using a Gaussian filter, so the weight is accordingly, right? It's a symmetric weight, right? So that is how we can smooth the data, right? Smooth across one line. Is that clear to everyone? Okay. So then it would look something like this, right? Pre-smoothing, post-smoothing, and again, like if there were, maybe this is not a good example, if it was a time series with noise, you could have seen that it would look more smooth, but this is the actual data, so it doesn't look as nice, but that's the idea, that by using these kind of weighted Gaussian filter, you can smooth the data. So this is done in one dimension, right? Now, um, um, if instead of, you can also change the effect, right? You have signal, but let's say it was gray matter, white matter, gray matter outside the brain. Yeah, you have smoothed the data, but because of the way you have smoothed, now differentiating gray matter from white matter will be more difficult, right? Because for especially around the edges, you have computed values where you have used both gray matter and white matter to come up with a measure, right? So um, as I had mentioned, by doing this, you certainly improve the signal to noise ratio, but your spatial resolution becomes worse, right? You won't be able to easily differentiate between them, right? So this is all in one dimension. Now you can think about it in two dimension, right? So this one was for one dimensional. This one is in two dimension, right? Where you have a Gaussian curve um, in a like in a two dimension, like instead of a bell curve, the two dimension would be a bell, right? Like any direction would be a Gaussian distribution. And the third dimension also in a Gaussian distribution, right? So in that case, so in this case, how would this work? Can someone tell? So I explained to you how the Gaussian distribution works along a single line, right? 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 You do for every element, do from beginning to the end. So please tell me how, if I were to do it in two dimension, how would I go about doing this? Yeah. What do you mean by dimension? Oh, mm, right, right. So technically you can do that, but there is easy, so easier way, right? So what you can do is, oh, So maybe for, let's say we can think of it as, let's say, okay, let's just assume 0.7, 0.15, right? So the center is 0.7, everything else is 0.15, right? So this is a 3 by 3 kernel, right? So that one was 7, but let's first assume this one, right? So it is 3 by 3, and then you have your image, right? Um, let's just assume we are using this image, right? So what we would do is, for the first element, right? Um, for this image voxel, we would take this multiplied by this, take this value multiplied by 0.15, right? This two multiplied by 0.15, and then add them up and substitute this value, right? So we have a new value now, whatever the value was. For this one, what we do is take the original value, multiply by 0.7, 0.15 with the original value, right? Then 0.15, 0.15, 0.15, 0.15, add them up, then substitute this, right? And so we keep repeating this till the whole data set is filled up, right? Again, if you have MATLAB, uh, so that is how you can do for the whole image, right? So here you had, let's say, time, so you could go plus and minus in time. Here you can go plus and minus in space, right? So both along x-axis, like maybe a simple way to think is that in this case, you can go along the x-axis, positive and negative. In here, you can go both x and y-axis, right? And that is how you add up, right? And that is what gives rise to good smoothing, right? And increase the space, increase the signal to noise ratio, but it becomes, you lose spatial resolution. Like it will be more difficult to separate finer structures. Let me see if I have time, I can show it to you in MATLAB. Right, so and then you can do the same thing in 3 dimension, right? So instead of this, you could have it 3 by 3, right? 9, where the center could be 0.7 and surrounded by 0.15, right? So, and this is just showing how we can use this, you know, to detect activity, right? And like different people have different opinion about this, but I feel that you should not smooth more than you need to, right? Because you are not really gaining anything, and you are basically, in this case, maybe especially this case, like, are you really adding more value than this one, right? So the question is, should you should you do spatial smoothing? The advantage, as I mentioned, is that it increase it increases signal to noise ratio, and then, you know, um, it uses this concept of matched filter, where the maximum increase in SNR by filter with the same shape size as the signal, right? So for example, if I know I want to remove my respiration rate, I can just design a filter that can remove my respiration rate. So it has, you know, it can give a lot of benefit to the signal, and my signal to noise ratio would increase. Also, when you are using smoothing, it reduces number of comparison, like, because it reduces your degree of freedom. So whether you're using Bonferroni or other method, it would be, it reduces number of comparison. Also, it may improve comparisons across subject, right? And it would increase or it would improve comparisons across subject, because based on the variability across subjects, right? Um, like, individual variability may be, if we don't do any kind of spatial smoothing, whatever individual variability there is across subject, you may not see those, right? Because different persons' sulcal and gyral pattern would be different. So by using a little bit of smoothing, you would be able to see those. As I have mentioned many times, the disadvantage is that it reduces spatial resolution, and it is challenging to smooth accurately if shape or size of a signal is not known, right? Any questions? And so there is this quote by a famous physicist called Ravi Menon, and his point is, why would you spend $4 million to buy an MRI scanner, then blur the data to make it look like a crappy PET image? Right? So the other way to reduce noise is by temporal filtering, right? As we have discussed, with Fourier transform, right? Um, if we have, let's say, a signal like this, we can decompose into a sinusoidal, random noise, and a low frequency noise. And right, so maybe one could also have had a linear drift, but this is how you can decompose the noise, right? So if you can do this, then it's easy. You can say this is drift, this is noise, and this is what we are interested. And so suddenly your signal to noise ratio would significantly increase without you having to do any kind of smoothing, right? So for this one, you need to know the temporal and the spectral feature of the data, right? So another way to think of it is in terms of Fourier analysis. And as I had mentioned, like, with Fourier analysis, we assume that any signal can be decomposed into a series of sine waves and cosine waves. And as I had said, to describe a sine wave, you just need 3 parameters, right? They are, and the phase, amplitude, and the very good, frequency, right? So once you have those 3, you can describe that. And this is just showing how, if we get a signal like this most likely has only 3 components, this one which has a large magnitude, this one and that one, right, with differing magnitude, right? And right, so okay, again, this is just showing amplitude, frequency, and phase. And so any waveform can be decomposed into a series of sine waves, right? So if you have this, right, so on. So for a square wave, the frequency spectrum is a sync wave, but for most physiological data, luckily for most physiological data, like the respiration, heart rate, and others, are fairly periodic in nature and can be used to identify and therefore separate them, right? So again, if this was the original data and the frequency looked like this, maybe we could use a low pass filter like this, right, and remove it, and then we would get a signal like this, right? And then if we high pass the data, we would get a signal like this, and the frequency spectrum would look like this, right? So as I had said, like for in resting state, most of the papers, they use a band between 0.01 and 0.1, right? And it's between 0.01 and 1 because if there is a drift, then setting a threshold at 0.01 is going to exclude those drift. And after 0.1, you have your respiration and heart rate that is used to exclude them, right? So initially for my paper, I used it because I wanted to make sure that the respiration signal and the heart rate signal was not contributing to the correlation, and that is why I had removed. But now, like as I showed you today, that is really not necessary, right? And I had done just to convince the reviewers that like what I was seeing was not an artifact, right? And then you can look at different frequency ranges to see if there is any specific frequency spectrum that we can see, right? And as I mentioned with multiband, where you can collect data, so now we can go as fast as like maybe 400 millisecond, right? So like every 2 seconds, we can collect 5 sets of data points. So in that case, we can also collect the heart rate, right? Which brings us to the next topic, which is called Nyquist limit, right? And the Nyquist limit simply says that if you are trying to measure something which is occurring at 1 hertz per second, I'm going to upload like later today all the PowerPoint, but please don't like I will upload the PDFs, but please don't circulate, right? Or you know, so what it says is that if you are sampling if you're collecting a signal which occurs once, like every second, like let's say heart rate, then if you collect data every second, will you be able to measure the signal or not? So let's say um, my heart rate was 60 hertz, right? And one of you got a pulse oximeter which measures data every second. Will you be able to measure my heart rate? Anyone? How many say yes? Yes? How many say no? Okay, one person. Good. Why? Okay, but why? That is the right answer. So according to Nyquist theorem, if someone's heart rate is 1 second, then you should collect at least two times, to be able to detect. But it should be, if it's less than that, you won't be able to observe it, right? Can you explain why? Say. Everyone is your friend here. Uh, say, no? Okay. So think of it this way, right? So let's say, like here, to cover one cycle takes how much time? 1 second, right? Now, if I was collecting one data point per second, right? And let's say I collected here. I collected the first data. The second data point I would collect is here, right? And then, so yeah, first data point, second data point, third data point, fourth data point. My goodness, if you were collecting my heart rate, you would say this guy is dead. It would be a flat line, right? So, but what would happen if you collected at least two times? Would you be able to see that, right? So it should be at least two times, right? So like, again, I know there's a lot of information, but just remember, because like if you do not just fMRI, but other modalities also, this would come in handy. So just remember that if your signal of interest is X, right, you have to collect at least two times in that time period to be able to observe the signal, right? And perhaps now you know why in fMRI there is no study which talks about alpha wave or gamma waves and theta waves, right? Because fMRI cannot even measure the heart rate, right? Because it's too fast for most fMRI techniques, right? It's like we are collecting at 2 seconds. We can measure the respiration rate, but not even the heart rate. Is that clear to everyone? Right? So so everyone understood Nyquist theorem in time, right? So now, can you explain to me the Nyquist theorem in space, right? So if, like, so what is the meaning of Nyquist theorem in an image? Right. So let's say the smallest spatial location. So let's say I want to study um, a region whose dimension is 1 millimeter by 1 millimeter, right? 1 millimeter by 1 millimeter by 1 millimeter. Or let's assume it's a two-dimensional image where my interest, that region is 1 millimeter by 1 millimeter. What should be my spatial resolution to be able to detect that region? Say that again. I can't hear you. Okay, there's a big difference, right? But but okay. So speak it loudly, like so. Very good. So if it's 1 millimeter by 1 millimeter, then your spatial resolution must be zero point 0.5 by zero point 0.5. If it's more than that, you won't be able to reliably detect that region, right? So if someone writes, so if there was a tumor which is 2 millimeter by 2 millimeter, then the spatial resolution that is absolutely needed is 1 millimeter by 1 millimeter, right? Good. So in time, it is twice as fast, right? In space, it is twice as less. Okay. Okay. Again, just to say that, these are the reasons why we cannot collect fMRI, right? Okay. Um, so for the resting state data, um, you have the low frequency, heart rate, harmonics of the heart rate, and respiration, right? So that is why we use a cutoff, or I had used a cut, um, you know, we had used a cutoff of zero point 0.1 hertz, right? But again, I just want to emphasize again that although I had used, that is not necessarily the right way, right? If you want to analyze the data now, maybe you don't have to even do filtering. If you have enough data, you don't have to do filtering because you can perhaps see what is happening to the respiration signal, right? Or you could do low pass versus high pass, right? Just showing again, right? You could, this is the original data. That's the frequency spectrum. This is using the low frequency spectrum. You can run the correlation analysis. And then for the high pass filter data, this is how the frequency spectrum look like, right? This looks much noisier, right? So maybe corresponding to respiration signal. And then, so this would be, you could take any time series signal, decompose into low pass, high pass, do seed-based analysis, and see what do you get, right? Do you think it could be an assignment for you guys tonight? Okay, do the thing I said, maybe for the weekend would be good. Okay. Um, right, so again, as I have said, you can use like this has a drift, right? If there is a drift, there are different ways to correct for it, and you can use, try to fit you can try to fit to a linear drift and remove the effect, or you can also do this in terms of the frequency spectrum, right? As I had mentioned, like if something is like that, the frequency will be very, very like a very low value. And that is why we use 0.01, right? So by using 0.01, we can get rid of the linear and quadratic term and have basically have a flat pattern, right? Reduce any kind of drift. And then the frequency would be like this. Again, like using different, you have the raw power and then after linear drift removal. Again, if you think you have different frequencies, right, you can compute the frequency and look at the frequency spectrum and see after you remove it what is happening to the frequency spectrum, right? So in this case, we removed the drift, but the frequency spectrum, because it was at such a low value, the rest of the frequency spectrum is not getting affected, right? Further, right, you can see by removing this that there are, different cycles which are present. The yellow is, right, 3 cycles, and the green is 2 cycles, right? Or there is this brown which is 1 cycle, right? So you can again use this filtering to identify specific frequencies and then analyze them accordingly, right? And you can see like, okay, which are the dominant ones, which are noisy, right? And we can describe in terms of the frequency value. And again, doing this, we can focus on any specific frequencies, right? So this one is occurring 1, 2, 3, 4, right? So if we want to study this signal, then we can find an appropriate filter that would only allow that frequency to pass through and exclude all other frequencies, right? And so the process by which you can select specific frequency is called like a band pass filter, which can be used to either allow specific frequency to pass through or reject specific frequencies to pass through, right? Right. So in this case, how would, like, if one was to, this is the raw, you remove the, like, a linear trend, and then this is, you are allowing a specific frequency to pass through and look at how the frequency signal is, right? And so again, based on the question you want to ask and the question you are interested in answering, you should look at the signal and look at, like, decompose into different frequency pattern and then see what would happen if you blocked specific frequency or if you allowed specific frequency, what would you see, right? And in my opinion, especially in clinical application, sometime looking both in time domain and frequency domain is useful because, as I said, if someone, let's say, had epilepsy, right, or where there is epileptical, um, when someone has epilepsy, increased firing and so on. So we don't really know, whether it is noise, whether it's related to epileptic discharge. So maybe a frequency component can give us some idea, right? Similarly, for other applications, if you're looking at the data, right, and you can look and see whether between two groups there is any difference in the noise structure, right? So just as an example, let's say we scanned two groups of subject, right? Um, 5 to 8 year old and like 18 to 21-year-old. And I found that between 5 to 8 years of age kids, their signal was much noisier. What would it tell me? Like if, like, let's say um, I scanned two groups of subject and we found that the younger group, the time series was much noisier. What assumptions can I make, or what guesses would I make to explain why the signal is noisier? I will give you one example, one possibility, that maybe these are kids, therefore they moved more frequently, right? Any any other explanation? Very good. So differences because good. So because especially young kids, the heart rate and respiration rate is very different from adults. So, and it is faster. So it will get aliased and will be noisier, right? So we cannot always assume that it is head motion. It could be that it is heart rate and respiration, which is making the signal noise, right? So in that case, that is information that we can use, right? If we know this is heart, well, we cannot see the heart rate, but the respiration, we can see what is the rate. And if we know that, like for kids, it is 0.3, while for adults, it's 0.2, then we can use a band reject filter to get rid of those frequencies. Okay. Any other question? Okay. Right. Again, I think we can look through this. Okay. So the other source is to like moving variance from noise to signal, right? So predictors of no interest, often there is variance that is known but not particularly interesting. We can create predictors that account for this variance and thus remove it from the residuals, just like the example I gave. Common example, regressors for experimental component, motor responses, instruction period, error trials. Regressor for known sources of noise would be motion, respiratory cardiac signal, and unknown noise sources. Also, just because you can assign something as predictors of no interest, a lot of times is not a solution in itself, right? And noise sources do not always match their measurement. Motion can lead to transient effects. which can include derivatives, and pony utilized degree of freedom, and including too many reduces statistical power, right? So like for head motion, like the example we did, we use 6 parameters, right? XYZ, and then rotation. Many have also used 6 additional parameter, and that is the derivative of the 6, right? And they think it gives a better fit, right? Because motion is transient, so the derivative would be, good indicator. You can do that. People can also have tried shifting and then doing the derivative. Then it's not 12 but 24, right? And you can always do that, but remember, as you add the number of noise regressors, you are reducing your degree of freedom, right? And as you reduce your degree of freedom, getting significance becomes more and more harder, right? The order of pre-processing steps is also important. Just as a like, why should you run motion correction before temporal pre-processing? Example, linear trend removal, right? So I have already like told you the answer, and like I should have asked, like, if you were to do motion correction or linear trend removal, which one would you do first, right? It is always motion correction should be done first, and then linear trend removal. Can you explain why? Because the right, the trend could be an, like a byproduct of head motion, right? So you first do the motion correction. After motion correction, if there is still a trend, then you use trend removal. Otherwise, if you do trend removal first, um, after you do motion correction, there may be some other trend that may show up, right? Um, so if you be careful about how you run the steps, right? And some steps should be done before others. And even like this is where it's a little tricky, because even among software packages, there is differences in opinion as to how things would be done. Dipabi has a different idea also, as some of you had mentioned about Dipabi. So the steps they suggest is image reconstruction, distortion correction, motion correction, slice timing correction, um, and then spatial smoothing, statistical analysis, spatial normalization. This is how FSL and AFNI do. For SPM, spatial normalization, spatial smoothing, and then statistical analysis, right? Um, so you can, as long as you are consistent how you are doing it, it is okay. But just remember that you use the same order of operation for all your subject, because if you change in between, it most likely is going to introduce some artifact, right? So the main points are that, as I have said, look at your data, um, like look at every subject. I don't know how much it costs to acquire a subject here, but in US to acquire one subject, I typically have to spend like $2,000, because the scanning cost is maybe $600, no, $700. and then to get a subject, also have to hire. What happened? Yeah, I know. Yeah. Um, yeah. And lucky you. Right. Yeah. Yeah. But throughout the country. Okay. Okay. Yeah. Okay. Um, anyway, yeah. As again, I cannot emphasize more that you should always look at your data, right? Um, you have spent so much uh, effort to collect one scan, right? If not you, others have spent so much effort to collect the data, like getting a subject, putting them in the scanner, running the subject, and then getting the data. So please, please, please look at the data by yourself, right? Also, like make scripts. First, look at the data, but have scripts that you run so that you know exactly the sequence of steps that you had used. Also, work. Um, well, if you have a physicist, that's great. To minimize physical noise, right? You can set up your parameters which will allow you to minimize the noise, right? Um, then design your experiments to minimize physiological noise, right? Again, if you are trying to scan um, a subject and you are using TR of 3 seconds, maybe that is not the best way to collect data because you're taking more time, right? If you wanted 100, like 200 data points, that would be uh, like 10 minutes, right? But if you used 2 seconds, it would be much faster, right? So do that. Um, like motion is the worst problem, right? Um, again, I wish I this is easy, but a lot of times for clinical cases, we we cannot we cannot throw out the subject. And I can say that once I had asked a friend of mine to be a subject, and he, like, after a lot of complaining, volunteered. I scanned him and I took him out, and then he said, where do I throw the gum? Right? So for the entire time he was chewing a gum, and it's like, you know, anyway. So like little things like this, you have to be very careful. Also for pre-processing, um, have your like hypothesis in mind. Think as you have collected the data. Also, like as you collect data, I would suggest you to start processing and checking, right? Sometime, you know, you may have made a mistake and you could quickly find out. I know someone who scanned 50 subjects, and after they had finished the study, they realized that there is a button for fat suppression which is used. They had forgotten, and because they had forgotten on the first study, they had simply copied the parameters. So the 50 subject was just, they could not use it, right? um, yeah. So okay, it's 3:40, so if you have any questions, I'll try to answer, or else maybe you want to show FSLI. Come, yeah. They should get, the student should get their money worth, right? will program. What happened? What happened?
Okay, so is is it fine if I show now? Okay. So if you want to visualize any image, it can be structural, functional, or any kind of contrast that you have generated. I am going to show T1 as sir has suggested. So you can just open this. As you can see that you will be able to see all these options. Just need to go to FSLIs. So it will just take some time to open. So once that is done, you can just go to file and see there are a lot of things you can add. There is an add from file, add from directory. You can also add standard. For example, if you want to like show an MNI template or visualize an MNI template, you can just go to standard and you can choose any of the MNI template that you want. For example, I'll just go for MNI T1 for 1 millimeter. So this is the MNI template where the voxel size is 1 millimeter, and you can see all the slices, coronal, axial, and sagittal. And if you want to see any image that you have obtained from your machine, so the first thing is I am just showing a nifty image which is not actually obtained from the machine directly. So when you get the images from the machine, they will all be DICOM files and they will not open in your like FSL interface. So I'll just first show how you can open a nifty image, and then you have question you can ask me. So this is one of my participant. As you can see, these are the like tasks that they have done. These are the 3 conditions that were there, and this is the anatomical file in the anat folder, and there are 2 images. One is T1, which is the image that we obtained from the scan, and another is the brain, which is the skull stripped one that comes after brain extraction in FSL. So if you want to see T1, this is the T1 that you can see, and in case if you want to see the skull stripped one, it's the same folder you can open and you can go to the skull stripped one and you can see this. Other than this, in FSLIs, you can actually see different types of atlases. For example, if we do it on the same MNI template that we were doing, so you just open a standard MNI template and you can see there is an option called settings, right? So you go to settings, then you go to ortho view, and there is an option called atlases. So you can go to that atlases option and see a lot of things, a lot of atlases will open at the below. These are different atlases that you can use. So I'll just go with the one I have worked with because I can show it better. So what I am using is, okay, so these are these are the atlases that you can open here. And if you want to choose anything from within the atlas, there is an option for show or hide. So if you choose show, that part will light up. If you choose hide, that part will go away. So that's, you go to settings, there is only one option, it's called ortho view. Oh sure, let me just open it again in that case. So you have to go to settings, ortho view, and you have to turn on your atlases option, and you will see all the atlases that are there. So there is atlas information, there is atlas search, there is atlas management. If you go to atlas search, you can also go for much more atlases. For example, there is a JHU ICBM white matter tractography atlas, which I have used. And see, if you open that atlas, here you will see the different tracts that you can highlight. So if you go and click on these, see, these regions will light up. Okay, so that's mostly what you can see, unless you have a contrast, which you also can visualize. And I don't have that data in my system right now, so I can't show you. But also for the color coding, there are a few things that you can do. So I'll just show you that. So I'm opening the standard again, and here you can see a grayscale, which you can color code up to your choice. Okay, and you can, here you can change your brightness, contrast, opacity. And if you actually are using a Mac, you can render the image. So basically what I'm trying to say is, okay, so if you see this is clear. Now if you go to view, and if you want to get a more rendered image, which you can directly do in Mac, but in my system I can't do for some reason. So what I do is I usually try to create a 3D view, and this comes with a better resolution. But if you have a Mac, you can render the image. There is an image rendering option in this particular settings, this button you see, and you will be able to see a very clean and um, like, I'll say, clean image. Yeah, that's, I think, is all. So yes, yes. Yeah, there are yeah, you can export it. You can so you go to setting. Yeah, there is an atlas management which you can just go below, right? So do you want me to show from the beginning how to open it? You just want to choose one atlas from it, right? Externally, if you want to add any atlas, in FSL. I think there are few atlases which you can actually upload on FSL and work, but there are not many of them which is compatible with it. In SPM, you can include, I think, any atlases. I'm not sure. I have not worked with SPM much, but I think yes. Okay, but if you suppose want to visualize your structural or functional data on FSL and you want to confirm the regions, because you have to overlap whatever you have obtained on your own FSL system, right? In that case, you will have to probably work with these atlases. And yeah, so I think that's all. This is just for visualization, like I think you can see this, right? So all the options are there. You can do brain extraction from this. You can do noise reduction, different types of noise reduction from this. So this is just for you visualizing your data at each step. So from the very beginning of your analysis, the first thing you should do is you visualize your data first, and then you go for example, if you have your T1 before brain extraction, before performing the BET, you should actually look at it, and then you do BET, extract the skull, you skull strip your image, and you look at it again. So FSL you need for the visualization, and in the end, when you are doing ROI analysis or any other kind of analysis, you will need FSLIs for that.
So the idea is that while with Google Colab, you could run, but running some of these things is taking a lot of time, right? So the idea is that if you like the codes and so on, perhaps best to run it on your computer, or at least once you get the data, right, download it on your computer and then use FSLIs to display, because it could be much faster rather than running through Google Colab. It could be because Google Colab is calling FSL things, and you would be doing it.
This you can use for all sorts of visualization. Absolutely, yes. Yes. For any data. Yes. It's called fossilize. The actual name of FSL is fossilize. So it was primarily created for looking into the mummies and fossils and how old they are and carbon dating, all those things. It just works for this kind of data as well.
Okay, so please work on this.